I'm Amrita from Department of Electronics and Communication Engineering. My topic for complex analysis and special functions is concept of analyticity of complex functions. Introduction to analyticity. Analyticity refers to a property of complex functions that are differentiable in a neighborhood of a point. It is a central concept in complex analysis, impacting how we understand complex functions. The importance of analyticity extends to various fields including physics and engineering. Definitions of analytic functions. A function f of z is said to be analytic at a point if it is differentiable at that point and in a neighborhood around it. This means that there exists a power series representation of the function around that point. Analytic functions are often referred to as holomorphic functions in complex analysis. So in the right side we can see the analytic function. So here is the definition where a function f of f is analytic at z0 if the following conditions are fulfilled. F is derivable at z0. There exists a neighborhood V of z0 such that f is derivable at every point of V. Definition. A function which is analytic on the whole of C is called an entire function. Theorem. A polynomial function is analytic at every point of C, i.e., is an entire function. A rational function is analytic at each point of its domain. Conditions for analyticity. For a function to be analytic, it must satisfy the Cauchy-Riemann equations in a domain. These equations relate the partial derivatives of the real and imaginary parts of the function. If the conditions are met, the function is guaranteed to be differentiable, hence analytic. Cauchy-Riemann equations. The Cauchy-Riemann equations are given by u of x, v of y and u of x not equals to minus v of x. So in the right side we can see the Cauchy-Riemann equation where dou u by dou x equals to dou v by dou y and dou u by dou y equals to minus dou v by dou x. Here in the left side we can see the equations of ux equals to vy and uy equals to minus vx, where u and v are the real and imaginary parts of the function. F of z equals to ux comma y plus x comma y, vx comma y. Satisfying these equations is necessary for a function to be analytic in a given region. Geometric representation, interpretation. And analytic functions have a geometric interpretation related to conformality. They preserve angles and the shapes of infinitesimally small figures in the complex plane. This property makes them essential for mapping and transformations in complex analysis. Power series representation. An analytic function can be represented as the power series in the neighborhood of its points. The form is f of z equals to a naught plus a1 z minus z naught plus a2 z minus z naught plus so on. This representation implies that analytic functions are infinitely differentiable. So here we can see for the given function f of x equals to tan inverse zx, these are the question for finding the power series representation of f by integrating the power series of f dash. So using this formula we can solve the following question. So this is the power series representation. Examples of analytic functions. Common examples of analytic functions include polynomials, exponential functions, and trigonometric functions. These functions are differentiable everywhere in the complex plane, hence they are analytic. Each of these functions can be expressed as the power series. So here we can see the trigonometric function graphs of sin x, cos x, tan x, cosecant x, secant x and cot x. So these are some of the examples of the analytic functions, which are polynomials, exponential functions and trigonometric functions. Non-analytic functions. A function can be non-analytic due to discontinuities or singularities. For example, f of z equals to fraction of 1 of z is not analytic at z equals to 0. Identifying non-analytic points is crucial for understanding the behavior of complex functions. Analytic continuation. Analytic continuation is a technique to extend the domain of an analytic functions. This allows us to find values of the function beyond its original definition. It is a powerful method used to explore deeper properties of complex functions. So this is the analytic continuation. Isolated singularities. An isolated singularity is a point where a function ceases to be analytic but is analytic in the surrounding region. These singularities can be classified as removable, pole, or essential. The classification plays a significant role in complex analysis and function behavior. Removable singularities. A removable singularity occurs when a function can be redefined at that point to make it analytic. This happens when the limit of the function exists as you approach the singularity. Functions like f of z, fraction of sin z by at z equals to 0 exemplify this concept by removing the singularities. Poles. A pole is a type of isolated singularity where a function approaches infinity as it approaches that point. The order of a pole indicates how rapidly the function diverges. For instance, f of z equals to fraction 1 of z minus z naught power n has a pole of order n at z naught. Essential singularities. An essential singularity is characterized by behavior where the function does not approach any limit. According to the Cassority-Weierstrass theorem, near an essential similarity, the function can take on any value. A classical example is f of z equals to e power 1 by z at z equals to 0. So these are the essential similarities. Entire functions. Entire functions are a subclass of analytic functions that are analytic everywhere in the complex plane. Examples include polynomials and the exponential functions. These functions are particularly nice because they have no singularities in the complex domain. Analytic functions and integrability. The integrability of analytic functions is governed by Cauchy's integral theorem. This theorem states that the integral of an analytic function over a closed curve is 0. This property leads to the powerful results such as Cauchy's integral formula. Here in the right side we can see the analytic function f of x equals to z of mod z. Cauchy's integral formula. Cauchy's integral formula provides a way to compute integrals of analytic functions. It states that f of z is analytic inside and on a simple closed contour. Then here the equation is as follows. So the right side we can see an example of using the Cauchy's integral formula of evaluating z square minus 4z plus 4 by z plus I, where C is the circle, mod z equals to 2. So here by applying the Cauchy's integral formula, we get the answer as pi of minus 8 plus 6i. Applications of analytic functions. Analytic functions have applications in fluid dynamics, electromagnetic theory, and quantum mechanics. The properties facilitate solving complex problems in these domains effectively. Understanding analyticity allows for better modeling of real-world phenomena. Summary of key points. Here we studied the analyticity is a crucial concept in complex analysis defining a large class of functions. The Cauchy-Riemann equations serve as the key conditions for analyticity. Understanding both analytic and non-analytic functions leads to deeper insights in mathematics. Coming to the further reading and resources, for a deep understanding, refer to Complex Analysis by Lars Ahlers. The online resources such as MIT OpenCourseWare offer free courses on complex analysis. So these are the further reading and resources of the complex analysis. Thank you.